So those are just a bunch of inequalities I showed you, but the best way to maybe understand what's happening right here is if you draw this flow over a cylinder. Okay. And you get something like this that we see experimentally. Let me draw that down a little bit. So this is a classic image you have of flow going over some cylindrical thing. Could be a sphere too. We'll look at a cylinder. So right here is my U of S. Right, let's focus on this streamline right here. And then there are a bunch of different points we can look at. There's going to be A, B, around here C, E, and then let's say like EF. So we're just sort of tracking along the surface of this whole cylinder, and you can kind of see how these relationships go around, right? So sort of right from A to C, you have the situation of accelerating flow. Right, it's getting faster as it goes along in there. That implies so from A to C, sort of like in this section, it's accelerating, and this is favorite accelerating. That gives you D PDS. Right. Acceleration is the same as this, so this is favorable. Why was it favorable? It's favorable because of this part right here with this shear stress increase as you get along there. Now, I had a classmate that, that's all fine and dandy. I had a classmate once that told me this, and I could never actually forget it, and that is like, I could never remember actually if it was accelerating or decelerating, but he said, like, what if it was like, just imagine it's just like a pipe, and like you can kind of see if you, like, if it was closed, right, you would see kind of right around here, as soon as you, right from here, at this point A, you have this contraction, and I always remember that flow rate's area times velocity. So I see that this like cross section is getting thinner, so it's got to be speeding up. If I just think about the fluid right in between there, so there are these relationships of derivatives and inequalities. But I actually just look at this picture. If it was an exam or something, I always did that. I just remembered it was like a pipe, and if I'm looking right past the stagnation point, I would see that the area is contracting. So that means the velocity has to go up to have like a constant flow rate between those two streamlines. I don't know what I mean, but right. So it's just a way to always remember if you draw this picture, wait, which part's accelerating and decelerating? Some people have other ways. Some people intuitively, I guess, know, but I always, because it's the negative sign, so I guess I always forget, but it's okay to figure out ways to help yourself remember something. But then, in that same reason, you can kind of see how now that's expanding right now, right? So now I have this like minimum area kind of expanding in this cross section to like a maximum area. So same with internals, pipe flow stuff, I know that my velocity is going to be decelerating. Okay, so now from C to E, you have the other case where now, what do we say? This is now decreasing. So that, and this is adverse. So now the pressure's going up as you go along here, right? High pressure means low velocity. Low pressure means high velocity. So, right, and the consequences of this is now that my boundary layer has started to grow. Right, likewise, boundary layer started to grow. There's an inverse. And I have this situation where now this is decreasing. So there is a situation, it doesn't seem like it's going to ever stop decreasing, because if I look at the streamline, it's just going to go on to this way. If it was Stokes flow, it actually would come back perfectly right on there, but then different laws would govern these things. So this is a situation where you kind of have to ask yourself, what happens when, if it's decreasing, what's going to happen if that, right, if the shear stress of the wall goes to absolutely zero? So here's a graph right here. If this is it was infinite, right? So what happens here? I kept decreasing, right? So I can just keep decreasing long enough such that the value of shear stress at the wall goes to 0. Well, we want to talk about velocity profiles all the time, right? So here's a velocity profile, right? If I look really close to these boundary layers, right? So, right, the definition there is actually a consequence, right? That would mean that because that would generally just be shear at the wall. So this idea of if I know my shear stress is decreasing as I go along S, eventually this shear stress at the wall would have to be 0. Now what does that mean? Well, that means that the gradient in terms of y direction would actually be 0. So it would not look like this, but you would get the situation where now it's doing something like that, where right here, if I draw my tangent, it's 0. So maybe flip it on its side. Maybe. It looks like that. I just flipped it because some people were confused about the internal flow 0 derivatives. But right, so then right at the point y equals 0, now my velocity profile starts to look like this. Okay, now right here, my tangent right here, now that's 0. So that's going to be strange. And all of this strangeness is right, kind of helps describe this garbage that happened afterwards. That's the idea of boundary layer separation. So that's right. We say that condition, equivalent conditions, or that is the point of boundary layer separation, when the shear stress at the wall goes to 0 or at this. So you gotta remember, think of it as S. So this would really be a theta so one coordinate that works well for the cylinder is actually this coordinate theta. So S is really a theta, but the idea is just along the streamline went 0. Same with this. So next I'm gonna unwind this and draw like sort of the developing velocity profile, because it helps me kind of understand what happened there.